Hello, this is the section 2.6 lesson. In this section we're going to introduce the idea of a function of a random variable. And at first glance the definitions we give in this section will look rather complicated, but as we'll see, calculations of these definitions aren't going to be that bad. So let's motivate this idea of a function of a random variable with a simple example. Suppose a man is injured in a car wreck. The doctor tells him that he needs to spend between 1 and 4 days in the hospital, and that if x is the number of days, its distribution is given below. So this distribution tells us that there's a 30% chance the guy is going to spend 1 day in the hospital, a 40% chance he's going to spend 2 days, and so on and so forth. Okay? So x here is a random variable. The man's supplemental insurance policy will give him $500 plus $100 per day in the hospital to cover expenses. How much should the man expect to get from the insurance company? He's going to get at least $500, but he'd like a better idea of what he can expect to get based off of the given information. Okay, so first let's define a random variable, y to equal the amount received from the insurance company. This is a random variable because he doesn't know exactly what he's going to get until he actually goes in the hospital. Okay. Now first let's list some different values of y. Well, if he spends 1 day in the hospital, then he's going to get a total of $600. If he spends 2 days in the hospital, then he's going to get a total of $700, and so on and so forth. Okay. So in terms of our original function x, y is equal to $500 plus $100 times x. So he's going to additional $100 for each day that he spends in the hospital. So here we have this new random variable y defined in terms of this original random variable x. That's the whole idea behind a function of a random variable. It's a new random variable defined in terms of an original random variable. Now, we still haven't answered the question. The question is, how much should he expect to get from his insurance company? And so here we've listed the distribution of x, and then the values of x and the associated values of y. So we want to calculate the expected value of y. By definition of expected value, we're going to take each value of y times its associated probability. Well, y equals 600 only when x equals 1. X equals 1 with probability 0.3, so we're going to take 600 times 0.3. Likewise, y equals 700 when x equals 2, x equals 2 with probability 0.4, and so we take 700 times 0.4, so on and so forth. We add that up to get 710. So there's our expected value. Now, it doesn't mean that the man is going to get exactly $710. In fact, that's impossible. This is just a theoretical expected amount. Okay? Now, if we take a step back and look at what we really did here, what was the 600? Well, the 600 was 500 plus 100 times 1. What is 0.3? Well, that's f of 1. The 900, what was that? That's 500 plus 100 times 4. 0.1, what's that? Well, that's f of 4. So what we did here is we had a function of a random variable to calculate the expected value. We took each value of our original random variable, plugged it into the function, took it times the associated probability, added them all up, and we're all done. That's the basic idea behind our next definition. So it says let x be a discrete random variable with range r in PMFF. Also let u of x be a function of x. So u is not the same thing as mu. U is just the name of a function. The input is this random variable x. Okay. The mathematical expectation or expected value of mu of x is denoted this, e of mu of x, and it says we take each value of mu times the associated f of x and add them up, and we're all done. And again, we have this qualifier that it has to converge absolutely, which we won't worry about. Okay, so that's the whole idea there. We have this function. We take every value of the function times the associated probability, add them up, and we're all done. So let's illustrate this with an example. And so it says let x be a random variable with this distribution. Okay, so it takes values -2, 1, and 5, and here's the associated probabilities. Now we're going to use this distribution in the next example as well. And so let's calculate expected values of a couple of functions of this random variable. So let's take the function x squared and calculate the expected value of that. So by our definition, we simply need to take each value of x, square it, times f of x, and add them up. So -2 squared times 0.25, 1 squared times 0.5, 5 squared times 0.25, add them up, we get 7.75. So that's all there is to calculating the expected value of a function of a random variable. Okay. Here's another function, x minus 1 squared. So we need to take each value of x, subtract 1, square it, times the associated probability, add them up, we get 6.25, and we're all done. Now let's list a few properties that this idea of mathematical expectation satisfies. And these properties are going to look somewhat similar to things we saw like back in Calculus 1. So x is a discrete random variable. Whenever these expectations exist, the following three properties hold. So number 1, if a is a constant, then the expected value of a equals a. Hopefully that makes sense. The expected value of a constant should be the value of that constant. Second, if a is a constant and u is a function, then the expected value of a times that function is equal to a times the expected value of that function. So in other words, we can pull a constant out front, just like we can pull a constant out front of an integral. And then third is somewhat similar to 2. If a1 and a2 are constants and mu1 and mu2 are functions, then the expected value of a1 times u1 plus a2 times u2 is equal to this. So we can break this up as the sum of the expected values. We can pull those constants out front, and we're all done. And that's very similar to the linearity property of integrals that we saw back in Calc 1. These properties make it very easy to calculate expected values of a function. So let's go back to this random variable that we just saw in the previous example. And first of all, let's calculate the expected value of this random variable. So take the expected value, take each value of x times its probability, add them up, we get 1.25. Now let's calculate the expected value of 3x plus 4. Now we could do this using the definition of a expected value of a function like we did before, but we can simplify things by using these properties. So what we have here is really one function plus another function. So by my third property, I can break this up as the sum of the expected values. Now in this first expected value, take the 3 out front. The expected value of a constant is just that constant. So now we have 3 times 1.25 plus 4, and we get 7.75, and we're all done. Okay. Another example, here we're going to do a little bit of algebra before we start applying those properties. So we want to take the expected value of x times x plus 2. So first of all, let's distribute the x across to get x squared plus 2x. Now we're going to break this up as the sum of the expected values. Now the expected value of x squared we calculated in the previous example to be 7.75. Here the expected value of 2x, we take the 2 out front. 2 times the expected value of x is 2.25. Using our results from part A, we add them together to get 10.25, and we're all done.